Hi, and welcome to week 2. Last week we distinguished machine learning from other approaches to AI and learned more about reinforcement learning, a way of machine learning that is managed through rewarding and punishing an agent. But this is not the only way a machine can learn, so today we want to learn more about supervised learning, the most common way of machine learning. And to begin with, our task is not getting bitten. We are animal keepers in a zoo and responsible for feeding the monkeys. The monkeys look very cute, but we have to be careful because some of the monkeys are biting. We already know which of the monkeys that are currently at our zoo bite and which ones don't. But however, there are new monkeys coming to our zoo and joining the group of monkeys. And we need to find a way to figure out which of those new monkeys bite and which don't, preferably without getting too close to their teeth. So what we have here is a set of monkeys for which we know whether they bite or they do not bite. The monkeys differ in certain characteristics, we call those features, such as whether they show their tongue, even how many eyes are open, or the shape of their eyes. Now it's our job to find a set of rules based on the monkey's features which help us to determine whether new monkeys arriving at the zoo are biting or not. You can now pause the video and try to find those rules by yourself. Okay, so let's try to figure out those rules. If we compare both groups, we see that only monkeys that have egg-shaped eyes bite. So this might be a good starting point. If a monkey has egg-shaped eyes, we classify him as biting. But only using this distinction is not enough. We still have some monkeys that are biting and have no egg eyes. So let's refine our rules further in the next step. We also see that only monkeys that smile but don't show their teeth are biting. Actually, this is an even better feature to distinguish the monkeys, because with the egg eyes we only account for 2, while with the smiling we account for 3 biting monkeys. Did you come up with something similar? We can also represent our 2 rules in a different way. As we've seen, whether the monkeys are smiling or not is the best feature to distinguish biting and non-biting monkeys, something we call the highest information gain. So first of all, we label all smiling monkeys as biting, and for those monkeys that don't smile, we now take the egg eyes into account. What we've created here is what we call a decision tree. And a computer might have created such a tree by repeatedly splitting the data according to the features, similar to how we did it. So to better see this, we'll now color all biting monkeys with a red background and leave the non-bitings as they are. First of all, the computer would find the best feature to distinguish the data. In our case, blinking wouldn't be such a good feature, but whether a monkey is smiling is. So the computer would split the data into monkeys which are smiling and those which are not. Now it would analyze those 2 subsets. First of all monkeys which are smiling. So all monkeys which are smiling, they are actually biting. So the computer can stop here and end this particular branch of the tree. Then it has to look at the other remaining subset of monkeys and would check whether it is done for this branch as well. As there are still monkeys that bite as well as monkeys that don't, the computer has to continue. Once more, the best feature is identified, in this case the egg eyes, and the data is split accordingly. Now all monkeys with egg eyes are biting and all without are not, so those branches can be ended as well and the tree can be considered complete. We held back some of our monkeys in our zoo to see how good our decision tree is working out. So let's see. Okay, so we have a feature smiling being false, egg eyes being true for this monkey. According to our rules, this monkey should not be biting. As this is just testing, we can get a feedback if that's correct. And it is. So let's repeat this for the next monkey. So for this monkey we have the feature smiling, so according to our rules, our monkey should be biting. As this is just testing, we know that this is correct. Let's repeat this for the next monkey. So we have the feature smiling being false, egg eyes being also false. According to our rules, our monkey shouldn't be biting. As this is just testing, it gives us feedback and it's correct. This monkey is not smiling. The first feature we used to decide is false, the second one exercise is true. This we would label it as biting. But as this is test data, we get feedback if we are right. And in this case, this monkey is actually non-biting. So our model would get this one wrong. Let's see some more examples. So overall, we had a rather good success rate, with 7 out of 8 monkeys being correctly labeled. But as this was just a simple example, we have provided you a more complex one that you can do in the additional materials. Still, we can now use this model to apply it to new monkeys coming to our group to classify whether they are biting or non-biting, to not get too close to their teeth. And with a success rate of 87.5%, we can be quite sure that we don't get bitten too often.
Let's recap our approach. We had a bunch of monkeys for which we knew whether they bite or not. Then we focused on certain features of those monkeys to find rules, when a monkey bites and when not. We then tested our set of rules with more monkeys, for which we knew whether they bite or not, to assess how good our rules are. And if we let a computer do the work, we would call this supervised learning. Prerequisite for the use of supervised learning is the availability of labeled data, which we call training data. These can be, as in the example of a robot, geometric shapes with the labels A, B, C or D. Or, as we had it in our previous task, the pictures of the monkeys, which are labeled as biting or non-biting. With a little luck, we can fall back on existing datasets. With less luck, we will have to label the data that we want to use as a basis for our model ourselves. From these labeled inputs, the algorithm finds a pattern to match the input, for example the shape and color, or whether the monkey is smiling or not, and their labeling, for example A or biting. Essentially, it creates a set of rules that allows the assignment of the feature to the label and refines these rules step by step. Since the labels of the inputs are known from the training set, the learning process can be supervised. The procedure receives feedback whether and to what extent the established rules already provide the input with the correct labeling. On the basis of this feedback, the rules are adjusted accordingly in order to gradually achieve a better result. In our example, we noticed that only looking at the x-eyes was not sufficient. Therefore, we improved our rule set by adding the rule regarding the monkeys smiling. This step is also called training phase. The model for a robot, the wooden template, represents the entirety of all rules, which should provide the input received with the correct labeling. These rules can be represented explicitly as a decision tree, as we did it with our monkeys, or more implicit by the parameters of a neural network, for example. We will learn more about how to do this with neural networks next week. In practice, satisfactory results usually require a large amount of training data. In the case of general image recognition, this means tens of thousands of images of cats and dogs. After the training is completed, the model can be used to label similar new data. For example, the robot can now use its template to label further geometric shapes. A supervised learning process trained to distinguish cats and dogs in photos can now also be used to label unknown images of dogs or cats, even if the viewing angle or lighting conditions of the photo differ from those of the training set. However, before such a model is actually used, its performance, its accuracy should be determined. For this purpose, it's a good idea to retain some of the labeled inputs that were originally received is so-called test data. These are now used to check how well the procedure labels these inputs, which have not been used for the learning process so far. That's what we did with our monkeys as well. Depending on the intended use, one is satisfied with different levels of accuracy of the model. For example, 60% correctly labeled test data may be sufficient for playing out advertisement, while an accuracy of 90% and more may be expected for recognizing images. In supervised learning, it's important to focus on those features that help us distinguish the inputs between different labels. Some of these features, as in our case, whether the eyes are X-shaped or not, provided much more information regarding the monkey's interest in biting people. If we would have focused on the color of the fur instead, this wouldn't have helped us at all. Taking more features into account helps us to distinguish between the monkeys, as for each feature we have one more dimension in which the monkeys can differ. You might wonder, why not take all features available and find rules accordingly? So let's build a giant set of rules, in which for every combination of monkey features from our training data, we would give the respective answer. We would have something like, if the fur color is brown and both eyes are opened and the teeth are bared and the tongue is not shown, the monkey is non-biting. And this for every of the 12 monkeys of our training data. If we do this, we lose any chance to generalize our training data and apply it to new unknown inputs. We would only be able to classify monkeys correctly that look exactly like those in the training data. Essentially, we would have memorized the training data. For every other monkey with a slight difference to the training data, we would have no clue. We cannot say if the monkey has X eyes based from our training data, this indicates that the monkey is biting anymore. We call this phenomenon overfitting. And as we have already seen, one use case of supervised learning is to classify data. Classifying means that the procedure sorts inputs into different predefined categories. This means assigning a label to them. In case of the monkeys, with our model, the decision tree, we can classify whether a so far unknown monkey is biting or non-biting. And according to our rather high accuracy, we are optimistic that this is actually the right category. Now we want to classify whether something is a fruit or a vegetable, based on the proteins and calories of each input. Once more, we have labeled training data. So for each of those inputs, we know, given their protein and calorie values, whether it is a fruit or a vegetable. As we have only two features, we can visualize the data like this. Now we once more can find rules based on our training data to distinguish between fruit and vegetable. One approach might be to draw a straight line that separates the vegetables from the fruits and adjust it for every further input of our training data. We might have started based on this data with something like this, and notice with the next input that we need to adjust our line a bit. We got feedback and supervised the learning process. We could take all of the data into account at once as well. Now the objects close to our straight have the maximal distance to it. Our rules are now described by the straight line, which we would call a hyperplane. If a new unknown input has more proteins and less calories than indicated by the line, we would classify it as vegetable, and the other way around. And if we classify data like this, instead of decision trees, we are using so-called support vector machines as a supervised learning algorithm. Obviously, in reality, most of the time, a simple straight line is not enough to separate the training data. We need more sophisticated mathematical functions to separate between different categories. And As with our monkeys, we normally probably wouldn't get a 100% accurate model. Additionally, we might have more than 2 categories. For example, we might want to classify multiple types of fruits. And as we've already learned, we normally would use more than 2 features. And we'll have 3, 4, 50, or 100 dimensions. We can visualize this, but the idea and procedure of classifying remains exactly the same. This way, in practice, we use supervised learning algorithms to classify whether an email is spam or not. Or we can identify viruses such as COVID-19 based on computer tomography images of people's lungs. And obviously, in image recognition, we classify whether a picture shows a cat, a dog, a bird, a human, and so on. We will learn more about image recognition in the unit about neural networks. In addition, supervised learning is used for tasks in which inputs should be assigned to a numerical value rather than a predefined label. We call this method regression. And we could use this to predict the price for real estate, given its area in square meters. Our training data consists of houses and their respective area in square meters as its features, and their price as its label. We would now try to find a line that fits all of our training data best. This means that the overall distance of all inputs to the straight line is minimized. This way we could predict a certain price for a so far unknown house given its square meters. In practice, we will often have a hard time approximating data. That's why we tend to use more complex mathematical functions to describe the relationship in the training data. Whether we use a straight or a different function, this obviously isn't a very realistic data set. Most of the time, we have more features to take into account, such as the location of a house, its year of construction, and so on. With this, once more, we have a lot of more dimensions, but get way better predictions. Furthermore, regression can be used to predict whether a user will cancel his subscription for a streaming service, or even to try and predict developments on the stock market. Today, we learned about the second way machines can learn, supervised learning. In supervised learning, we have a lot of labeled training data. Those inputs have a certain amount of features, like egg-shaped eyes in the monkeys, or proteins and calories with the fruits, and a label, such as biting or fruit. By processing the data, the computer tries to find patterns and rules to match the features and the labels. This matching pattern represents the model. Before applying our model in practice, we would test our model by using it with test data we hold back from our training data. And if we are satisfied with the performance of the model, we can use it on new unknown data. Furthermore, we explored some of the algorithms used for the supervised learning, such as decision trees, support vector machines, or linear regression. Obviously, there are many more algorithms used for classification of data or regression that can help us classifying animals on images or find out whether a mail belongs into the spam folder. Moreover, they can estimate selling prices of real estate based on specific features or predict developments on the stock market. And in our next video, we want to actually implement a supervised learning algorithm in Snap to have our program distinguish between monkeys that bite and monkeys that don't.